Hey, so we have some information today that's kind of like a lot of math. But I'm thinking, Keith, just keep me on track. Keep asking me, like, why do we need to know this? So
I absolutely will.
it's actually pretty cool. So what we're going to talk about today is sort of the situation where there's reflections. And we talked about it a little bit in the class the other day, and we're going to talk about it some more in the skulls lecture. But there's some math here that's really interesting where we can talk about, why is there a sign change and what's the order of magnitude of those reflections. And then there's some special cases where you have two reflections, like, for example, in the front surface of the skull and the back surface of the skull. And then lastly, there's the special case of the matching layer on the transducer. So I don't want to get into those. And this is just kind of what we talked about the other day, where we said that there's the reflection at an interface. And so if you look at a fat liver interface, then you can see that there's not very much reflected at all until you get up to these larger angles over here. And then you can see that there is this big reflection right here. And so that's kind of what we call the critical angle. But what we're more interested in is the reflection at bone. And you can see that the critical angle there is much, much lower. Now it's about 25 degrees or something on that order. And so what I want to do is kind of get into the derivation of this because it's kind of interesting, actually. But don't let me be boring. Keep me on track here. Okay, so I have to say this outline is just terrible because like there's like equations in the outline, things like that. But it's pretty much what I told you about. We're going to talk about normal incidence, then we're going to talk about non-normal incidence, and then there's going to be these special cases where there's two reflections. And then we're going to talk about sort of like the skull special case and then the matching layer special case.
So
Okay.
when this is over, though, the students should be able to objectively look at a problem with ultrasound and say, how do I get the most energy through the skull? That's the point, right?
Yeah, that's a possibility, or at least to understand what the issues are. And then the other thing is that when we talk about safety, we have to make approximations for how much goes across the skull, and then what is reasonable to assume. What are our reasonable assumptions? So this is going to come up again in terms of safety.
Yeah, well, real quick, it is interesting you're saying that. I don't think you have to make estimations about how much gets through the skull. So Kim will teach you about this later, but the FDA doesn't want to know. They don't care. They want you to assume there is no skull. And that sort of limits how high you can go.
Well, so there the assumption, if you're assuming that there's no skull, is that you have a lot of transmission and you're going to have a lot at the focus, and that's going to overestimate how much is there, and it's going to be very safe. If you keep that number under some limit that's set, that'll keep you very safe. But the question now is, we could get in a situation where we've overestimated so much that we've titrated the power so much that we don't really get very much in at all. And then we might not be efficacious. So this is a situation where we don't just want to be safe, we want to be efficacious as well. So we want to have a really good estimate. And now the question is, like, how do we get a good estimate? So first of all, just today, let's figure out what the issues are. And then later lectures, we'll talk about how do you get better estimates. Okay, so shall we go for it?
Yeah, jump in. I'm still here.
I don't know if everybody can notice, but Keith got a new microphone, and he's sounding pretty good there. Okay, normal incidence. Yeah, we can see that on the screen. Normal incidence here at an interface. So this all arises because of acoustic impedance differences. We mentioned this the other day, and this is a table showing you that for some different materials here, the densities are different. That gives the speed of sound is different. But remember, the speed of sound isn't linearly related to the density, but it's sort of the square root of 1 over the density. And then there's the bulk modulus term, which it's related to the bulk modulus. Okay, which is 1 over the compressibility. We talked about that in the other lecture. And then when you multiply the density and the speed of sound, then you get the acoustic impedance. And so what we see right there is that there's big differences between, say, this group right here, the fat, the aqueous soft tissue. Those are very small differences, but there are big difference between those in air and then those in bone. And so what we're going to see is when there's big differences in the acoustic impedances, that there's going to be big reflections. Okay, so just a little bit more in terms of definitions. Let's say you have two materials with different acoustic impedances, and you have an incident wave, that's a pressure wave that comes in. Then there's going to be some reflected from that interface, that's the reflected wave, I'll call that PR, and some that's transmitted, so that's the pressure wave that's transmitted as PT. All right, so some more definitions. The reflection coefficient, and when you're talking about the pressure, is just the pressure that's reflected over the incident pressure. And so that's the fraction of the pressure that's reflected. And of course, now we have TP, which is the fraction of pressure that's transmitted. We can also talk about intensity. And so there's the reflection, the fraction of the intensity that's reflected. So now it's R, which is the reflection coefficient, but it has a sub I for intensity. And then there's the TI, which is the transmitted fraction, but now it's got the sub I because that's the intensity. Okay, and of course they're going to be related to each other. We'll talk about that relationship. Now, one of the really key things to remember, and what I'm going to tell you on this slide, half of it's going to make a lot of sense. You're going to go, yes, of course. And the other half, you're going to say, what? So the first part is the part that makes a lot of sense, and that is power is a conserved quantity. So what we're going to have here is that the power that the second time is the power that is transmitted plus the power here that's reflected, and that's equal to the power in the beginning, which is the incident power. So if you're talking about intensity, then you say that the transmitted intensity and the reflected intensity is equal to 1, where we've just said that the incident intensity is 1. Okay, does that make sense? You're silent, Keith. No, wait, I can't hear you. You're on mute somehow.
How about now?
Okay, good. Yeah, all right, is that making sense?
Yeah, it sounds good.
Okay, so then I'm going to tell you the part where you're going to say what? Say what? And so this is the part where pressure is not a conserved quantity. So here what we see is that the pressure on each side of the boundary must be equal. So on the one side, you have the pressure that's coming in, the incident pressure, and then there's the reflected pressure. And that equals now the transmitted pressure, because you have to say that the pressure on this side equals the pressure on that side. So we have, let's say our incident pressure is 1, then the reflected fraction plus 1 is equal to the transmitted fraction. So that's going to be something we're going to have to think about a little bit and make sure that we understand that. And again, it's because the boundary doesn't sort of supply any resistance. And so if it's going to be sort of in equilibrium, and the pressure on this side is going to be equal to the pressure on that side. Okay, with me there?
Yeah, I don't think we have an idea about this yet, but why should the students be learning about pressure versus power transmission?
Well, we're going to talk about both of them. They are both going to be super helpful and important. Pressure is sort of our fundamental quantity. When we put our transducers in a scan tank, we're going to measure pressure. Intensity is really important because intensity gives rise to a temperature rise. So a temperature rise can be proportional, directly related to intensity. When we're talking about radiation force, that's going to be related to intensity. And so the intensity is going to be really helpful as well. And then there's a relationship between them, and we'll get to that in just a moment. Okay, so what do we have here? The reflected pressure ratio. And so this is the pressure that's reflected over the pressure that's incident, and it's the difference between the acoustic impedances over the sum of the acoustic impedances. And so from that equation, now you understand why when there's big differences in acoustic impedances, then that's going to give a big reflection. The absolute value is going to be very big, but that number could be either positive or negative, depending on whether Z2 is bigger or smaller than Z1. So it could be positive or it could be negative. And if it's negative, then that means that the reflected pressure wave is inverted. So I'm going to have some examples here. So this is just now, we're going to have sort of a pressure wave that comes in that's sort of Gaussian shaped. It goes through first acoustic impedance material. And then at that boundary, we're going to see that there's going to be some reflection. And given the numbers that I've set up here, where acoustic impedance on the first material is 1 and it's on the second material is 2, then we see that our reflection coefficient, if we look at those numbers, is going to be 1/3. And so the amplitude of the pressure wave coming back that's reflected is 1/3. And it comes back, since that's a positive number, it comes back in the same sign. It's comes back as a positive. Okay, so now that's all going to get changed if we swap the acoustic impedances. So what we're going to do in the next one is we've swapped them so that now the acoustic impedance over here on this side is higher than it is over here. And now when we play this, you maybe are anticipating what's going to happen. We're still going to have the amplitude be 1/3, but what we see is that now there's a sign change. And that's just simply that Z2 here, we plug in the numbers, we get 1 minus 2, we're going to end up with a minus 1/3. And so that's what gives rise to that sign change. Okay, so we're going to get a reflection. We can figure out what the amplitude of that reflection is given these equations, and then also whether or not there's a sign change. So good. Shall we move on? Or?
Yeah, it is a sign change, essentially meaning that you've pushed the phase forward, like 180 degrees, if we're talking about sort of a circle. Okay.
That's right. So if we're just talking about sine waves, multiplying times -1 is the same thing as advancing or delaying it by 180 degrees or half of a cycle. Yep. And that'll come up in just a minute. So I'm glad you mentioned that. All right, so let's talk about the transmitted pressure ratio. And remember now, the equation goes like this, so that the pressure on the left side of the interface is equal to the pressure on the right side of the interface. So 1 plus the reflection fraction is equal to the transmitted fraction. So now what you may be thinking is, well, this number, if R is greater than 0, then the transmitted fraction, the transmitted amount could be greater than 1. And in fact, yes, that's true. So the transmission may be greater than 1. You could actually have a pressure wave that as it goes into the second material gets bigger. It's a little counterintuitive, but it's true. So here's the equation looks like for the transmitted fraction. I don't tend to like that equation so much because there's more numbers to remember there. And it's just easier for me to remember that it's 1 plus the reflected fraction. But you could do it either way. So let's look at the numbers. So here we're going to go from an acoustic impedance of 1 into acoustic impedance of 2, just example numbers that are not real. And what we see here is that the wave, as it's going towards it, it starts with an amplitude of 1, and then it's going to grow as it goes into that second material. And then the reflected part is what we saw before. So the reflected amplitude is going to be 1/3. The transmitted amplitude is 1 plus 1/3. So it's going to be 1.3. Okay, so a little counterintuitive that the pressure on that second material is in this case going to be higher. But that is true. And then we could say, well, what happens now if we swap the acoustic impedances so that we start out with something that's 2, and then it's going to now hit the interface with acoustic impedance of 1. You anticipating what's going to happen here, Keith?
No, I'm still thinking back on the previous part, trying to make sense of more pressure transmitted than what has gone in. Because pressure is directly related to intensity, right? Where you're supposed to be losing intensity
is the pressure squared divided by the acoustic impedance.
But I guess because you're changing the acoustic impedance, you may be lowering intensity, you're saying.
Because
or do both should go up, right?
So in this case, it's going to go up, right? So remember, so if what we have coming in on one side, let's say it's normalized to 1 is the incident pressure, and then the reflected pressure is going to be 1/3, then remember we have to say that the pressure on this side of the interface equals the pressure on that side of the interface. So now on this side, you're going to have the sum of those. So it's going to be 1.3.
Right.
Yeah. Okay, and then it's going to be different if now we're going to swap out those acoustic impedances. So we start in the acoustic impedance of 2 and go now to the acoustic impedance of 1. So what do we think is going to happen? We think we're going to start out with 1 because that's by definition, we're normalized to our incident pressure. What we saw before is that our reflected pressure is going to have an amplitude of 1/3, but there's going to be a sign change. So that's going to be a minus. And then when you sum those two, because the pressure on this side has to equal the pressure on this side, now we're going to see that it's going to be 2/3 on this side. Do you believe that's going to be true? Let's see if the math.
Let's watch that animation.
Let's see if the math holds up. Let's play our animation. We come in with an amplitude of 1. It's going to hit the interface. And what we see is a transmission of 2 and a reflection of -1. Sorry, a transmission of 2/3 and a reflection of -1. Okay, so at this point, this is just sort of fun. We haven't gotten to any real world examples, but we're going to get to those in just a moment. So, but before we get there, let's talk about intensity. And remember, intensity is defined as the pressure squared over the acoustic impedance. So using that relationship, then what we see here to get the reflection coefficient for the intensity is looking at this part right here. It's the ratio of the intensity that's reflected over the incident intensity. So now we have the pressure squared over here on this part of the equation, the pressure squared that's reflected over the acoustic impedance of Z1, and then divide now. So what we've done is we've put in the definition of the intensity is P squared over Z, and we can do that here as well, P squared over Z, and we just have different pressures we're referring to, and in all of these, both of these situations, we're referring to Z1. Okay, so then when you just simplify that, the Z's are going to cross out, and we're going to get the P reflected squared over P incident squared, and that's just going to be the square of what we saw before. And so this equation over here on this side is exactly what we saw before, but now it's got the square. And so the reflection coefficient is, for me, very easy to remember, is just the square of the reflected pressure coefficient. Now the transmitted intensity, remember, it doesn't have the same equation that the transmitted pressure equation was. And here what we see is that because power is conserved, that the intensity coming in, so that we define that as 1, is equal to the sum of the reflected intensity and the transmitted intensity, because power is conserved. So what happens at one point is equal to the sum of the other two at a later point. So okay, so using that, then you can derive the transmission coefficient, and it looks something like this. And again, I don't find this really all that much fun to memorize this. So I just like to remember this equation right here, so that if I remember what this is, then the transmitted intensity is 1 minus the fraction that I remember. So that makes it a little bit easier for me. Okay, so let's look at some numbers. And so we have a 2x2 table here. We've got pressure and intensity, and we're going to look at how much is reflected and how much is transmitted in several different situations. But first of all, what are the equations? Just to summarize what we've talked about so far. So in terms of the reflection coefficient and the pressure, it's the difference between acoustic impedances over the sum. And then you can come up with the transmitted pressure fraction by using that equation that is 1 plus the reflection is equal to the transmission. To go from pressure to intensity, we're going to square the pressure, divide by acoustic impedances cross out, and now we see the reflected intensity coefficient is the square of what we saw for the reflected coefficient for the pressure. And then we can come up with what the transmitted intensity is, and using the equation that we see right there, where the intensity is conserved. Alternatively, you could take this term right here, and using the equation that we're familiar with for how you define the intensity, it's equal to the pressure squared over the acoustic impedance. Now you can come up with the transmission of the intensity. It's a little bit of math. Don't want to go through that right now, but you can do it, and it all does make sense. So it is a relationship that works.
So you could use these sort of simplified views of things if you knew that your, materials were really homogeneous, right? Is this like, is this something you routinely use in your lab, Kim?
So yes, but I'm going to tell you about some more interesting cases in a little bit. Right now, what we've just done is set up what are the equations. Let me give you some examples. Here it is in my outline, examples.
Perfect.
Right. So our first example is liver fat. So let's say you're doing ultrasound imaging and you've put the transducer on the abdomen, and you've gone across the liver, and then on the other side, there's a little bit of fat before you get into the kidney. And you want to know how much is going to be reflected at that interface. Well, we can figure out what that is given the equations that we just looked at. First of all, what are the acoustic impedances? We see fat right here, we see liver right there. And this is, I guess, going now from fat to liver instead of liver to fat. So I got it the other way, but not that big a deal. And then what we see is that the pressure is that about 9% is going to get reflected back in terms of the pressure, which means that about if you then look at the intensity, then in terms of intensity, only about 1% is going to get reflected back. So most of the ultrasound beam is going to get transmitted through that interface. It's not really something that we worry about too much for ultrasound imaging. That soft tissue to soft tissue, whether it's fat, liver, kidney, those numbers are all very similar, and we're not going to have huge reflections. However, we are going to see big reflections when it comes to air and bone. Just to note, this is an example where if you'd followed through the numbers, that we see the transmitted fraction right here is actually greater than 1. So that can happen. Over here, the other equation that I told you about was the sum of these two components has to equal to 1, and that's what we see did happen here. All right, so let's get to something else that's more interesting. So what if you're doing ultrasound imaging and you put the transducer on the abdomen and you're pointing back at the diaphragm, and then you're going to have a lot of reflections at the diaphragm because that's the interface between the liver and the lungs. And so we can never image with the lungs because there's going to be so much reflection at the air tissue interface. What do the numbers tell us? Well, we set up the numbers. So here are acoustic impedances for fat. We could have used aqueous soft tissue instead. It doesn't really matter because those numbers are very similar. But we see the acoustic impedance for air is very, very different. When now we look at the differences between those, we see a large reflected pressure. And then the intensity as well, very, very large, almost exactly 1 reflected. So what that means is we're never going to be able to image the lungs with ultrasound very well. What does it mean for us in transcranial ultrasound? It means that you can't, for example, put your transducer on the forehead because there's a sinus behind your forehead before you get to the skull and then into the brain tissue. So there are locations that you can't put your transducer, and that's the fact.
So, I was going to say something I used to ask a lot, and Kim will talk about it in a little bit, is what if there are like, let's say, nanoscale dissolved gas bubbles? So technically you have an air interface, even if it's a small bubble, but it's very, very tiny. And what happens in that scenario? Kim, are you going to talk about that?
Yeah, but we're going to talk about that later in the course because it's sort of a little bit of an interesting and different phenomenon that happens when you have air bubbles, because we're not so much concerned with, there is reflection, but there's also the fact that with the ultrasound goes through these low pressure waves that the air bubble can expand quite a bit. So you can end up with this expansion of the air bubbles. And so they're both happening. You definitely can have both. Another thing you can have, for example, is if you heat up the tissue to the point of a sort of boiling, then the boiling will, it becomes sort of a gas, which is very much lower density. And so the acoustic impedance is going to go down. And if you're using ultrasound imaging, you'll see just a huge reflection from sort of the boiling tissue.
Mhm.
Okay, so let's talk about another example, and that is a fat bone interface. So let's say you put the transducer on the skull on the side. It's going to go through the skin, and then there's the subcutaneous fat, and then there's the bone. So this is actually a bit more relevant now. And what we see is our acoustic impedances for fat and for bone. Big differences between those, not as big as for air, but big enough so that what we see is now the reflected pressure is pretty big. At that interface, you're going to have about 60% of the reflected pressure, of the pressure reflected. What you see then is now the intensity, about almost 40% of the intensity is going to get reflected. You're still going to get some transmitted through. And because this is a situation where we're going from low acoustic impedance into high acoustic impedance, what we're going to see is that the transmitted pressure is actually going to go up from 1 up to 1.6, because it has, this number has to equal to 1 plus that number. Okay, I'm gonna have to work on my drawing a little bit. But we're going to see that number go up a little bit, and then we see our transmitted intensity is about 60%. So what that means on the front interface is we put a transducer on the skull, we're going to get maybe 60% transmitted through. On the other side, maybe about 60% transmitted through on the other interface. But I say maybe because it's actually really kind of complicated. And I wanted to get to that a little bit later in this lecture. Okay, so let's just say that there's a single interface. That's what's going on. You see that number is greater than 1. These numbers are going to sum to 1. And so that all makes sense. Okay, so we've started introducing some of these reflections and how it's kind of complicated, and especially when we get to the skull. Any questions before we move on here, Keith?
No, it looks like you're about to tell us what happens when you don't have a perfect sort of orthogonal collision, as was shown in all of your beautiful graphics.
Yeah, that's exactly right. You can imagine that you could put the transducer on the skull so you think it's pretty flat on the skull, so that the ultrasound's going to come in at a normal to the surface. But remember, and I'll show you pictures of skull and later, I've shown you pictures of skull. Certainly in the next lecture, I'll show you more pictures. The interior surface of the skull can be kind of not flat. I wanted to say corrugated, but I don't think corrugated is exactly the right word either.
Cardboard? Yeah, I don't think so.
You know,
Beveled, maybe beveled, or like rough. I don't know.
We'll see pictures and then we'll revisit this question, is exactly how to characterize it. But the point is that you're going to have non-normal incidence. And so that's why this part of the lecture is really important, because if you're not normal, and of course, normal means when the ultrasound's coming straight in, but if you're not on normal, but you're coming in at an angle with respect to the normal, so this is the angle right here, then what we're going to see is we're going to have a lot more reflected and less transmitted. So that's what I wanted to get into right now. So there's this is now showing you that the incident pressure is coming in this way, and then the reflected pressure, and then the transmitted pressure coming this way. But there is continuity of pressure, so that we have to think about continuity on this side and this side. Same thing as we saw before, because there's at equilibrium, that interface is going to be at equilibrium, so you have to have the same pressure on each side. And the other sort of boundary condition is that there's continuity of the normal velocity. So if there's a wave that's coming in from the left, then we have to look at the component of the wave that's this way. You could sort of, break this vector down into a component that's this way and a component that's this way. And we have to look at the component that's normal to the surface in terms of the velocity, and say that there has to be continuity of the velocity of the particles over on this side versus the velocity of the particles on that side. Otherwise, you might have particles moving across the interface, and then you're no longer sort of at equilibrium. So those are sort of our boundary conditions, just to kind of give you an idea where these come from. And then this is showing you what the equations are. A little complicated. Maybe there'll be some homework to work on using the equations. But what we can see when we use those equations is, well, you know, it's a little hard to look at it and say, well, of course, but we know that these are going to be true. The same equations that we had before, that 1 plus the reflected pressure is equal to the transmitted pressure. And that's going to be true in this situation as well. And then the continuity of power, so that 1 equals the reflected intensity and that plus the transmitted intensity. And then of course, these equations are going to hold on that side as well. Okay, so that's what gave rise to this figure that we've talked about before. And we could go back and we could say, well, let's plug in specific numbers. And you can see when you plug in the numbers, you know, what is the critical angle such that where the reflected coefficient, if you plot out what's the reflection coefficient, which we see over here on the vertical axis versus the angle, when we've put in the acoustic impedances for fat and liver, that angle goes up at about 70 degrees. Sorry, the reflection goes up at about 70 degrees. And so what that means, if let's say you're imaging the liver and you've got the kidney on the backside, and there's an interface between the diaphragm and the fat on the other side that gets up to around 70 degrees, then you can start to see reflections there. But that's a pretty high angle, so not something that we worry about a ton with imaging, but definitely very, very important here for the skull, where you can see that even very small angles here at 5 and 10 degrees, you start to see differences there in the reflection coefficient. And then you have 100% reflected when you get up to about 25 degrees. So again, that's not that important for maybe the outer surface, because people's outer surface of their skull is relatively flat, and you can position your transducer so that it's relatively flat up against the surface. But what we're going to see is going to have a big effect on the inner surface. It may have an effect if you may be thinking, well, I want to angle the beam, and can I angle the beam just by angling my transducer? No. That's not going to work all that well, because let's say you want to get to a part of the brain that's kind of, towards the anterior part, and you want to, put it right here on the temporal window and then angle the beam sort of forward. And that's not going to work, because you're going to end up now with an angle with respect to the normal.
Yeah, and that's not to say people don't try. I mean, there are companies based on moving an array or like tilting it relative to your skull. And people do that for like rats and animal models too. But Kim's here to show you why that might not be a great idea.
Yeah, and here you can see you can get away with small angles. And it's just that once you get, up to like 15 or more, then you're going to have a lot of reflection. And but it's interesting because this is going to depend also on the thickness. So I'm going to tell you about that in just a moment. It's kind of fascinating how thickness is going to play a role here. So just to sort of summarize what we've looked at so far, and that is if we look at the incident angle versus a transmitted angle, so there's not a one-to-one correspondence because there's going to be refraction. And so this is just on this side, the first plot, just telling you about the refraction angle. On the second, we're looking at the pressure ratios, so versus the incident angle. And so this is a fat skull interface right here. And so what we see is that the reflected beam as a function of incident angle is going to go up here and go up here at about 25 degrees. And then what we see is the transmission beam right there. And then, of course, there's the continuity of the equation. And so we might ask, well, is this true? And if you look at the numbers that you say that this is about 0.6, and then transmitted is about 1 plus that, and then that's true for all those different angles. And so this equation holds. And then when we look at the intensity ratio now, what we see is that the reflected intensity goes way up right there at that critical angle. So you can see right here. And then our equation is that as the reflected intensity goes much higher, then the transmitted is going to be, so the transmitted is going to be 1 minus the reflected. And so the transmitted now is going to come way down here at that angle. And so that equation holds as well. Okay, so where are we going? We've talked about a single interface, and now we're going to get to something really interesting, two interfaces. And so that's where we're going to have two reflections. And so this is going to be more like what we have with the skull. And so here's a little picture of the skull. And what we have, this is a CT picture. And we have, which side, Keith, can you tell which side is we going to put the transducer on?
We're going to put it on the left. I was going to say this does, I can see where you came up with like corrugated cardboard. It kind of looks like that.
Oh yeah, and this is the most corrugated. So what we see here, what Keith is referring to is how on this side it's relatively flat, and here we've got a bump. Well, we're going to see some that are going to be much worse than this. But what this is a CT picture, and this is showing us the skull right here in white. So with CT, bright pixels are going to be dense, and that's going to be the skull. This is our sub-Q, our skin and our sub-Q fat over here on this side. And then you can see that it gets a little bit dark over here, and that's just the air. And then this is going to be the brain over here on this side. Okay, so we have our beam coming in from the left. This is our pressure incident there, that interface. And a lot has just happened here. I set those animations up and just a lot happened. So what we saw happening was as the beam comes in here from the left, there's going to be an interaction at that interface. Some of it is going to get reflected and some of it's going to get transmitted. Now there's another interface, same thing happens. So let me just get rid of my scribbles and maybe just play that again. And what we'll see is that the beam's going to get split at each of those interfaces. Some's going to get reflected, some's going to get transmitted, and this is going to go on and on. And when we were talking before, remember you were saying, well, what about standing waves? Well, this is sort of what's going on in here is that you can end up with waves that get reflected and reflected around inside. And so then you can have, you know, a wave, a pressure wave that comes out that's sort of the through transmission. Let me get rid of my scribbles again. You can have a component that comes out that sort of, it just got transmitted all the way through. You can have a component that gets transmitted through that first interface. It gets reflected back from that second interface and then gets transmitted through, or maybe it gets reflected back twice and now gets reflected through, and so on, and up to infinity, right? So what you can end up is just a whole series of reflections, and then they're all going to add to our transmitted pressure. So now I just have a slightly different drawing here, and what I've done here is superimposed. Oh, now my animations are going really quickly, so I'm going to have to stop and and as soon as it finishes playing, I'll tell you what we saw, and then I'll start it again. Okay, so what we have here is our pressure wave that's coming in, and so you see this sinusoid. And then when it hits the interface right here, what we're going to see is the transmission as it goes from one acoustic impedance to the other one, the transmission is going to increase. And so where pressure wave is now increased right there, that interface. And then as you can see, it comes across our mock skull right here. And then at this interface, there's going to be some that's going to get transmitted through. And now it's going to lose its amplitude as it gets transmitted through. And so that's going to come down here, sorry, to this blue one now. This is the one that goes straight through. And some of it's going to get reflected back. Let me get rid of my scribbles and go on back and play that again. So, oops, now we're going to have to watch both animations again because they're kind of showing you the same thing, that you're going to end up with reflections and transmissions at every interface. Okay, so let's watch this. First wave comes in, and then there's going to be some reflection, and then that's going to come transmitted. There's going to be another reflection. So there's the component that's bouncing around, and it's going to come out. So now what I have is three components, and I'm showing you so we can actually kind of judge the amplitude of those. And we see the one that got transmitted straight through is the blue one. It's pretty good amplitude. The one that saw, you know, one set of reflections and then gets transmitted through is sort of the light green color. And then the one that went through twice is going to end up being the cyan color. And what happens now is the sum in sort of the steady state, where you have more than like, you know, one cycle here, where you've got several cycles going on. Then you have sort of a steady state. It's to be the sum of all of these. And what we can see now is that While you may have calculated that the pressure wave that goes transmitted through is going to be reduced, but now in the steady state where there's multiple cycles, they all sum up together. And actually, surprisingly, we're going to find out that they're going to sum to basically a transmission of one, which is a little counterintuitive because you're thinking, well, there's all these reflections and there's going to be some reflected back from the interface and et cetera. But it really is true that you can figure out through the math, and what the math tells you. Should I pause here, Keith? Am I boring you?
No, it's good. I'm looking at it and I'm just remembering that if we're looking at these, they're all coming out in phase, but they might not always, right?
Yeah, it's right. I have set this up so that they come out in phase. And that's exactly right, because I've set it up to be one cycle, that the thickness is equal to one cycle. But I will tell you about what happens when we vary the thickness in just a moment. But in this situation where the thickness is equal to one cycle, what we see is the component that comes straight through. So it's the incident pressure, and then there's the transmission coefficients. The one that's gone back through the material and then gotten reflected and then come through. So that's the light green one. It's equal to the incident pressure, the transmission through the first interface, reflected at the second interface, reflected back at that first interface, and now transmitted through the second interface. And now you can keep on going with saying, well, what happens to the third one? And so there's the transmission components are still there. The reflected terms now are there, but they're squared. And so now you're going to have multiple waves coming back. And each time that the transmission components are the same, the transmission coefficients are the same, but then the reflection coefficients are going to have another term. So they're going to get smaller and smaller each time. But then when you add them up, given that situation where you have one cycle, that the thickness is equal to one cycle, what we're going to see when you figure out all the math, and I'm not going to go through all of this, but just to let you know, if you wanted to, you could go back and look at the math. And what we're going to see is that these terms are here just going to cancel each other out. And we're going to get the transmitted pressure is equal to the incident pressure. And there's several things that are amazing about this. One of them is that this is true no matter what those acoustic impedances are. And that if you set it up so that the thickness is equal to one wavelength, then the transmitted pressure is going to be equal to the incident pressure.
Very neat. I can't wait to see how this unfolds. Well, I guess it's also worth keeping in mind that these equations work out really well when everything's perfectly homogeneous. So I think they're going to be useful in real life, but they're never going to quite work out in this way.
Yeah.
But it's better than nothing.
Right. But what I am doing is setting up why this is complicated.
Yeah. Oh, definitely.
Okay. So I said here that it had to be one cycle so that the thickness is equal to one wavelength, but that's not exactly right. And it's not just when the thickness is equal to one wavelength. I mean, it is true that when your thickness is equal to one wavelength, then the transmitted pressure is equal to the incident pressure, regardless of those acoustic impedances. But let's look at the relationship as we change the thickness with respect to the wavelength. And so this is what I just showed you, where the thickness was equal to one wavelength. And now what I'm doing is at the bottom, I'm plotting the transmission as a function of thickness over wavelength. So when thickness equals wavelength, that equals 1. And we get a value. I told you it was 1, but what I'm plotting here is something that's slightly less than 1. And that's because I only looked at the 2 of those reflections, so 3 components coming out on the other side. If I had done this with an infinite number of reflections and added them all up, it would have equaled 1. But I was getting diminishing returns. And so I stopped because I kind of got bored after 2 reflections and just included the 3 components. But just imagine in your mind that that's going all the way to 1. All right, so I did this simulation here. Now I'm going to reduce the thickness. And what we see is that it's changing everything. And in fact, just what Keith mentioned before is when they come out on the other side, they're not all in phase with each other. There's going to be some destructive interference over here on this side, and they're not going to sum up to the same amplitude. In fact, now, when we vary our thickness, and what I'm going to do is reduce the thickness. So here it was 0.9 of wavelength, 0.8 wavelength, and I'm plotting down below what the transmitted pressure is. It goes kind of through a minimum, and then it's going to come up again. And what we're going to see is that when it was half a wavelength, we got the same result. All that pressure comes straight through. And now it's going to decrease again. And then we're going to see as we go now towards zero thickness that it's going to come up back up again. So the key here is wavelength over 4. So, or n lambda over 2. Oh, yeah, not wave. I said the wrong thing. N lambda over 2. So it has to be a multiple of lambda over 2. So it could be lambda over 2. It could be lambda, 3 lambda over 2, or etc. Then you're going to have complete transmission no matter what those acoustic impedances are, as long as it's going from sort of Z1 into Z2 and then back into Z1. But what's really interesting here is the part that we didn't quite finish, which is what's happening as it's going now towards the thickness being very, very small, much, much smaller than the wavelength. And what we see is that we're going to get that 100% transmission again. And so a little counterintuitive, because like you could have something that's really small and there's still reflections. You think, well, there's still reflections. We saw the reflections before, but it turns out that you're still going to have 100% transmission, just like we did when it was wavelength over 2 or 1 wavelength. So it's a pretty interesting result that when a reflector gets smaller and smaller and is much smaller than the wavelength, it can kind of just ignore it.
Yeah, to me, it's always been like one of those things where if the math works out and says it works, I take it for, what it is. I have to believe it. Practice, I mean, I guess it works for like all the tools we've used and things. When there's just these really, really thin interfaces, you sort of don't see much happen there.
Okay, so this is our summary here where we have 2 reflections. The transmission depends on the ratio between the thickness and the wavelength. So you could have a material that has a different speed of sound. It has a different wavelength, and then it just depends on the ratio of the thickness to the wavelength. So the absolute thickness depends on what material is for that to happen. And then when the thickness is equal to an integer multiple of lambda over 2, then you get 100% transmission. When the thickness is much, much less than the wavelength, you get 100% transmission. So that's pretty fun. So here's a pretty cool picture. And now what I'm going to tell you is we just learned in sort of ideal situation, and Keith's mentioned this several times. Well, this is when you have a homogeneous material and you have a surface which is very flat and but this is not at all the situation in real life. And so what I've queued up here is some samples from CT pictures of different subjects. And what we see is on the left, there's one that's really thin and it's very bright, meaning that it's mostly cortical bone. And then we get into these other ones, then there's variable brightness and variable thickness. So over here, all the way over on the right, it's also very, very bright, although it's very, very thick. So this means it's mostly cortical bone. There's a little bit of trabecular bone in there, mostly cortical bone. And then you see these others. So this one right here is very thick, but it's got the cortical bone layer, a lot of trabecular bone, and then a cortical bone layer. Okay, so in other words, there's a lot of variability in here. And I'm going to tell you a little bit more about why that's important. But before I get there, let me just point out the other point we were talking about, which is the shape. So if you look at some of these, you see the outer surface is nice and flat. You can get your transducer right up against it, nice and flat, and be pretty relatively assured you're going to have pretty reasonable normal incidence. But then you can see on the other side that there's all those variations. And so if you maybe have normal incidence here, you may not have normal incidence in other locations and other parts of the skull. So it can be very, very complicated. So what we see here are areas that are cortical bone and trabecular bone. And let's think about this a little bit. Let's go through some of our numbers. So Keith, let's say we have an ultrasound beam and we're transmitting at 500 kilohertz. And then I ask you, what's the wavelength of sound?
I guess it depends on what the speed of sound is or what material you're going through, right?
That's exactly right. So if it's in soft tissue, it's 3 millimeters. What is it going to be if it's in bone?
So the speed of sound in bone, you told us, is about double the speed of sound compared to tissue. So the wavelength should also be about double.
That's exactly right. Good. And so the speed of sound is going to vary. This is a plot that came out of some of our work where we were plotting the speed of sound here on the vertical axis, and on the horizontal axis is versus Hounsfield units. And never mind the fact that there's these different colors in here. Let's just, what I want to point out from this is that the dots here, these came from different bone fragments from a couple of different skulls, and there was measured speed of sound. But what I really want to point out is that the velocity varies here from about 2,000 meters per second to about 3,000 meters per second. And so there's a lot of variation. And what we see is that it's kind of following this linear trend, so that at the lower Hounsfield units, and that's where we have the trabecular bone, it has a lower velocity. And at the higher Hounsfield units, this is the cortical bone, it has a higher velocity. But what's happening in the skull is that we have both cortical bone and trabecular bone, and irregularly shaped. So we have a whole range of velocities in there. So when you start thinking about what we talked about before, where if the thickness is exactly lambda over 2, you can have complete transmission. Well, what lambda are we talking about? Because there's a range of velocities. So, the wavelength in bone now is going to be something like 4 to 6 millimeters, given that range of velocities. And if it's 4 millimeters, you get one set of transmission curves. If it's a 6 millimeter wavelength, you get a different set of transmission curves. And in actual fact, what's happening here is the wavelength is changing as it's going through the bone. So the thing is, so ultimately, I think you could figure this out if you do a very good simulation and you kind of go pixel by pixel and you change the velocity and you figure out exactly what the reflection is at every pixel. Then I think with a nice beam simulation, you're going to get a good result. But I think if you just kind of go, oh, I'm going to take, a T1 weighted picture, I'm going to say that the skull thickness was 8 millimeters. I'm going to tell you, you can't really tell what you should do with that number, because unless you have more information about, is it cortical bone and trabecular bone, you just really don't know whether you're going to get a lot of transmission or, quite a bit in terms of reduction of transmission.
Maybe you could explain also why it's sort of important to have a phased array if you're going to try to use these simulations.
Yeah. Yeah, well, okay, so you're sort of previewing what we're going to talk about in later lectures, but why not? Let's say you have a transducer that's over here, and let's say you can split up your transducer into different elements. So let me just kind of picture it as a flat transducer with different elements in here. And so we're going to talk about the beam that's coming out or through these different pieces of bone. And you can see that through those different sort of segments of bone, it's going through pretty similar thicknesses of bone and pretty similar velocities, because again, if you look at the plot over here on the right, that those are all going to have sort of high Hounsfield units, and they're all going to be sort of similar. So they're all going to be sort of clustered up here, and they're going to all have very similar velocities. So the beam that comes out on the other side, if you look at the phase of all of those individual beams, then the phases of those are supposed to be little fees. I think I did a little better job with my
Nice.
scribbling. But the phase that comes out on the other side is going to be all very similar. So great, that's perfect. But let's take one of these others. Let's take this third one right here. And let's say now that we have an ultrasound transducer and we have these different elements, so that we have multiple beams that's coming through here. And then one of them comes through here. It looks to me hard to tell exactly, but I'm going to guess that the thickness right there is 5 millimeters. And then this one right here, it's going to go through maybe 3 millimeters. So it's gone through different thicknesses of bone. The velocity is going to be different. And so that means that when it comes out on the other side, now the phases of these two beams are going to be completely different, because they've gone through different speeds and for different thicknesses. It's kind of like, let's say you and I are driving down the highway for a while, and then no, we're going to start on city streets for a while, then we're going to get on the highway, but you're going to go on the highway for a mile, and I get to go 2 miles on the highway. And then at the end, we're not going to be in phase anymore because we're not going to line up because we've gone different distances at different speeds. You like that analogy?
Yeah, that was good. I was about to compliment you.
Oh yeah, thanks.
If you hadn't already complimented yourself. But yeah, that's a really important reason that people are moving towards these phased arrays versus just a single layer of ultrasound transducer.
Yeah, and then sometimes it's just fine to use a single element. And so especially, this is kind of interesting because you might ask, like, where on the skull did I take these pictures? Because oftentimes the part right here on the temporal bone is thinner than other parts and more homogeneous. And so it's called the temporal window. And so sometimes people feel like, well, I'm going to put my transducer right there. I can get nice normal incidence. It's going to be thin and I'm going to get a lot of transmission. And it's true that I would say it's I would put 99% chance you're going to have more transmission than if you put it in somewhere else, but it's not always true that you're going to get really good transmission, because sometimes you get a skull that looks like this one right here or this one right here, even on the temporal window. Window, I have to put that sort of in quotes because it's not always a good window. Okay, so cool. 2 reflections. And it can get complicated. And I think if you have like a nice beam simulation, then you could probably figure this out pretty reasonably accurately. And in the absence of a beam simulation where you want to make an approximation, it's going to get hard to figure out how to make an approximation. In terms of safety, you could kind of assume that you're, up here, that you're always going to have some sort of possibility that there's going to be transmission that's going to be very high. But it's just not clear exactly, just given a thickness. Okay, should we go on to the next topic?
Yeah, I think so.
Okay, I love that picture.
It's really good.
You might be asking other things about this, like why are there holes in the skull? I think that's a blood vessel. So you can kind of just approximate that as water. There's probably blood vessels that are kind of through plane as well as blood vessels that are in plane. You can get an area like this. This is really interesting. This is probably a suture. When babies are born, that their skulls have different plates, and then they kind of fuse together, and then the part where they fuse together becomes kind of calcified, and that's the suture. Mm-hmm. And so that's probably what we're looking at right there. Another funny thing that we're talking about skulls, which is completely off topic, is that when we're talking about those plates, that when babies are first born, that there's this little area right here at the top where there isn't any bone, and that's called the fontanelle, and it's nice. It's a nice acoustic window. So if you have to do an ultrasound imaging on a baby and you want to look at their brain, then you would go right there. As a parent, it's kind of funny because you can see like their pulsations right at the top of that spot right there, because their brain's sort of pulsing, and you can kind of see that. And it's always a little worrisome, like, oh, what if like they bump their head and it's right at that spot?
Yeah, it might be interesting to talk about applications at that stage in life, during your skulls lecture. I'd be interested to hear it, like what people would look for through the fontanelle window.
Yeah. Okay, we'll get to that. The other thing is that when people think about, and one of the things we want to talk about in the ultrasound imaging lecture is functional ultrasound, and trying to get sort of a picture of brain function by looking at blood flow changes. And when you want to do this in the brain, you have to think about acoustic windows. So you could maybe do this in newborns where you can get into the brain by the fontanelle. Okay, but that's a little off topic. So let's pull ourselves back. We're talking about reflections, and I have one more special case here to talk about. And in this situation now, we no longer have our 2 acoustic impedances in the beginning and the end being the same, but they're all going to be very different. And in this special case, what we're really going to be talking about is the transducer. And this is a very simple picture of a transducer where you have right here is the piezoelectric crystal, and then there's going to be electrodes on the other side. We'll get into this more in the hardware lecture. If you want to skip this lecture and kind of come back to it later, that's fine too. So we have our piezoelectric crystal, and then there's going to be electrodes on either side. Those are the gold. And on the front side, there's going to be a matching layer. And on the back side, there's going to be backing material. We'll talk more about why those are really important. But the key thing that I wanted to talk about is what happens when you're creating the ultrasound in the piezoelectric crystals. So you start the pressure wave here, and then there's the soft tissue, which is over here, and you really want to have the pressure wave transmitted into the soft tissue. But now, given what we already know, when we look at these acoustic impedances, we know that if we don't have a matching layer, we're just going to have a lot of reflections and very little is going to get transmitted through. In other words, if you just put that piezoelectric crystal right up against soft tissue, not very much transmission. So what we're going to do is we're going to put another layer in between, and this is called the matching layer, and it's going to have an acoustic impedance, which is going to be in between those two. And what's going to happen?
Is that a question, or I guess you'll just show them?
That was a little bit more of a rhetorical question.
Oh, gotcha. Okay. I'll be quiet.
But if you want to tell me what you think is going to happen, that's
no. I already know. I'm excited to see it.
Okay. All right. So we're going to have our pressure wave come in. Same thing that we saw before. There's going to be reflections and transmissions at each of those interfaces. And then ultimately, we're interested in what's the pressure that's transmitted. And it's going to be the sum of all of the transmitted pressure waves. And so they've gone different paths because some of them went back through multiple reflections. Again, you could kind of go through the math, but let me just kind of cut to the punchline here. And in this situation, what we have is the acoustic impedance of the first material, a piezoelectric crystal, is greater than that in the matching layer and is greater than that in the soft tissue. And because it's different, it's in that order that those waves that kind of got reflected once and then got, let's see, so got reflected at this interface, got reflected at that interface, that there was a sign change. And because there's a sign change now, then in order to have complete transmission, we're going to now say that this thickness has to be lambda over 4. But if we do that, then what we're going to expect is we're going to get complete transmission, just like we saw before in the other situation. It's just that our requirement now is that we're going to have lambda over 4 be our thickness in order to maximize that transmission. So it's pretty much what we saw before. It's just now the only difference is the thickness has to be lambda over 4 so that we can have a sign change when it comes out the other side, because there was a sign change on one of those reflections. So in other words, there's one more requirement, and that is that the acoustic impedance of that matching layer has to equal the square root of the product of the acoustic impedances of the transducer and the soft tissue. Sometimes in homework we could give out that as a homework question, how to derive that, but it's really just, it kind of makes some sense that you're sort of stepping down. When there's a big difference, you're going to have a big reflection. But if you can go through 2 interfaces with smaller reflections, then you're going to have more transmission. So it makes some sense.
Yeah, I love this too, because it's like super practical. I think it was after I took the course with you a few years ago now that I used the equation in one of my own little custom transducers. And if you use the hydrophone tank, you could actually see that there was, way more transmission after adding a matching layer.
Were you making your own matching layers?
I was, yeah.
Oh, what are you making your matching layers out of?
So it was a magnesium alloy, which is very stiff, but very low density metal. So it sort of fulfilled the acoustic impedance approximately. I mean, there's some wiggle room. Like if you're not perfectly at the geometric mean or whatever, it's okay, but you try to get as close as you can. Most people use epoxies, I think, like doped epoxies for this kind of thing.
And so those were your 2 candidates, or did you have other candidates you were looking at?
No, those were my 2. And the magnesium alloy just ended up coming in the thickness that I needed, which is like around 1 millimeter. Mm-hmm. Have you guys used matching layers in your lab, or?
Yeah, I mean, most transducers
Created them.
are, yeah, going to come with a matching layer. Yeah.
Oh, I mean, created your own for like some custom
No,
builder.
well, I don't know. You don't have to ask Jurhai about his. But okay.
Anywho,
No, remember,
how
we're
you do
giving a lecture
it?
right now, so let's try to keep on topic.
Sure.
Okay, so in fact, we're just going to wrap up here because we're at the end of of the lecture. So we've talked about normal incidence and non-normal incidence. We've talked about the situation where there's not just one reflection, but there's two reflections, and our special cases. So the special cases where when you have one material and then you go into a material of a higher acoustic impedance and then back to the original material or close enough, such as water, soft tissue, bone, soft tissue, and in between there's bone. Sorry, I think I said the wrong thing, fat, soft tissue, and bone in between. And as long as the thickness of that material is n lambda over 2, then you can have pretty good transmission. And that's also true when you have materials that have very, very small wavelengths, that you can have very good transmission. And then in the case where there's two reflections, such as the transducer and then the matching layer, that's our special case where you're going to have pretty good transmission when it's wavelength over 4. So I think we should wrap up there, but as we turn it off, let's talk a little bit more about transducers and matching layers.
You showed